All right. Parallelograms. What do we know about parallelograms? Okay. Any of those descriptions would work. So the tricky part is trying to figure out which point goes with which. Because I think once we get that figured out, all we have to do is find a couple of vectors from 2 or 3 points, and then we should be able to use a cross product and take the magnitude, and that's the area of the parallelogram. So the tricky part is trying to figure out which of these 3 vectors to use. Pat, you have a suggestion?
Yeah, if you look at points K and L, your x values are the same, and between L and M, your y values are the same. So you can include the full value coefficient.
All right. Do you guys get that?
No. Slower. Like more words. Please.
So so K and L have the same x value. M and N have the same x value. So those would probably go on those would probably be on the sides that we're looking at. The other thing about this is that somebody said triangles. Where's a triangle here?
Through the center, like from end to end.
Through any of these things would make a triangle, right? So I could either look at a triangle that involves K, L, and M. Oops. Or I could take a look at a triangle that involves the other one. I suppose we could take a look at a few other different views of triangles. But what this is telling me is that if we just take 2 of them, or 3 of them, 3 points, instead of all 4 points, because that's all we need to make up our parallelogram, right? We just need 3 points. So if we just ignore the last point and find relationships between 3 points, we can get the triangle. In fact, we can find the area of the triangle if we wanted to. What's the area of the triangle? It's just half of the area of the parallelogram, right? So we could just find the area of the triangle if we wanted to. So in any case, I think if we just choose, I think if we just use L, K, and M, and then find arrows connecting those, then we're probably going to be good. So let's do that. Let's find this vector from K to L, and that would involve subtracting those 2 points, right? So let's call this vector V, and head minus tail, we have 1 minus 1 is 0, 2 minus 1 is 1, 5 minus 2 is 3. And let's call this next vector W from K to M, and do the head minus tail again. So 6 minus 1 is 5, 8 minus 1 is 7, and 5 minus 2 is 3. So if we just take the cross product and find its magnitude, we should be able to find the area of the parallelogram. So we'll cross them. V cross W. And you guys know how to take a cross product, right? After yesterday's lecture, we're all pros. 0, 1, 3, 5, 7, 3. So in the I direction, you would cross out the i's, and then you have a submatrix 1, 3, 7, 3. The j direction is always a negative. Then if you cross out the jth column, the first column and the first row in the jth column, you have a submatrix here that's a 0, 3, 5, 3. And then if you cross out the kth column, you have a matrix 0, 1, 5, 7. So you find the determinants of each of these, and this first one is a 3 minus 7, no, 3 minus 21. 18, yeah, negative 18. I have a 0 minus 15. Will end up being positive 15, and a 0 minus 5. So that's my cross product. This gives me a vector perpendicular to V and W. So now all we have to do is find the magnitude of that. The magnitude is actually equal to the area. So area is equal to magnitude of V and W, which is the square root of 18 squared plus 15 squared plus 5 squared, which is whatever that is. Negative what? Oh.
Well, when you square it.
Well, the answer is not going to make a difference because you're squaring it, but it is negative 5 if you want the actual vector.
It's like 23.95.
574. Okay. So, hope that's right. Suppose we can check. Oh, so notice that when I clicked on this box, this thing popped up, so it doesn't want a decimal, it wants an actual value. What was it, 574? Okay, are we good? All right. So today we are supposed to talk about lines and planes. We talked about a plane already, right? We found an equation of a plane. But that's too much. What happened to my notes here? This is all just complicated looking. 12.5? Yeah. Does that say 12.5 up on top? Oh, this must be from another book. Ah, I don't have notes.
Just wing it.
All right, let's just wing it. Okay, let's start. Since we had that that example of the points, let's. Or here, let me start it this way. Since I'm just winging it. I'm recording. When you have to find an equation of a line, let's go back to the two dimensions. When you have to find an equation of a line, what did you need for an equation of a line?
Point and slope.
Point and slope, right? Now, so in algebra, when people take algebra, they don't always give you the point and the slope. What other possible thing can they give you to find an equation of a line? They might ask for 2 points, right? And we know that if you have 2 points, that has a well-defined line that passes through those 2 points. So also, if you're given 2 points, you can find an equation of line. Now, how do you find an equation of a line if you have 2 points? Find a slope. So you go back to this idea of finding a slope, right? And then we just need 1 point. If they gave us 2 points, which point do you use to find the equation of the line? It doesn't matter, right? Okay, now, imagine taking that idea where if you have 2 points, you have to find the slope, and then now you can use either point and the slope to find the equation of a line. Imagine taking that idea to 3 dimensions. So in 3D, we found an equation of a plane if we had a point and a normal, right? So if you have a point and a normal, we saw how to get that equation of a plane. Now, in geometry, if you had 2 points, you can find an equation of a line. If you have 3 points, then that should be a well-defined, you should be able to find an equation of a plane, right? But now, so now what we want to do is, let's say we're given 3 points. We should be able to find an equation of the plane. And back in 2 dimensions, what we did was, with the 2 points that we were given, we found the slope. And then we use either of the 2 points. So what do you think we can do with 3 points in space? So I want to find an equation of a plane. For an equation of a plane, we need a point and a normal vector. I have 3 points, so my point business is taken care of. So we just need to find a normal vector. So I want a vector perpendicular to the plane that these 3 points are on. What? Okay, so these 3 points can make up 2 vectors, right? As long as they're not all on the same line. So if we connect and make 2 vectors out of these 3 points, then we have two vectors that are actually on the plane, right? These vectors are actually on the plane. And when you cross those two vectors, you get a vector perpendicular to those two vectors, which is perpendicular to the plane. Okay? So now you choose any of these 3 points, and then you have a normal vector that you just found, and then you're all set. That make sense? All right, let's do an example. So let us make up 3 points in space. Just shout out some points. 4, 2, 2. 2, 7, 9. 3, 4, 8. Now, the only thing I would worry about if we're randomly picking vectors is that these points, randomly picking points, is that these points don't lie all in a straight line. Because if they do, what's the cross product of two vectors that are pointing in the same direction? 0. Angle between them is 0. Sine of 0 is 0. So the cross product is going to be 0. So if we randomly select 3 points, there's not a very good chance that they all lie in the same direction. But we'll figure it out anyways. And you guys all chose positive numbers, I noticed. You're all positive people, huh? So let's call a point P1 to P2, that vector from P1 to P2, let's call that V. And not that it matters, not the direction matters in this case, but give me the actual vector V going from P1 to P2. -2, that's 2 minus 4. -2. 7 minus 2 is 5, and 9 minus 2 is 7. So that's one vector. Now let's call this vector from P2 to P3, W. And what is this vector? What is it? 1, -3, -1. Now, if I look back at this and draw it out, my vector V goes from P1 to P2. And my vector W goes from P2 to P3. Am I going to have an issue with this? What? It should be tail, tail. But am I going to have an issue with this? As long as they're on the same plane. Coplanar. Oh, look at that word. As long as they're coplanar. Did you just make that up? No, that's an actual word. Coplanar, they're all on the same plane. As long as they all lie on the same plane, remember that vectors, the only thing that's important about vectors is its direction and magnitude, right? And it doesn't matter where it starts or where it ends, because you can always move vectors around. So we can move it tail to tail that way if we wanted to, but we really don't have to because it's all good. Yeah. Well, if this is the other vector that I was looking at, I can just move that vector over here, And now it's tail to tail. Yeah, but the numbers that I got here are the value, the components of the vector. So I can move it here if I want to. But, you know, moving it there is just my own visualization of it. Mathematically, it's not going to matter. Okay? We good so far? All right, so now let's cross those two vectors. So V cross W. Are you guys getting the idea of crossing? Are you guys getting good at it? Can you guys do this in your heads already? So I would imagine taking this and writing it on top of each other, and in the I direction, I would have 2 and you guys do this? Okay. So that's 6 minus 5 is 1. 2 minus 7. What's 2 minus 7? 5. Negative 5, and then there's a negative in front of that. And there's 6 minus 5. No. 5 minus negative 21. 5 minus negative 21 is negative 16.
I think if we said,
well, it does.
no, like mathematically, mathematically we use the components. We don't need to do it. We just cross them. We all use like this way and that.
So, the first one is negative 5. That was way off, huh? The first one was negative 5 minus 21. 16. The next one is negative 2 minus 7. That's negative 9, right? But it was negative, so it's positive 9. And the last one is negative 6 minus, positive 6.
That's 5.
This is 5? This is 5.
The 9 is the 5.
The 9 is a 5? And then the last one is what? Is that good? All right, so this is my cross product, and this vector now is a vector that's perpendicular to both of these vectors. It's perpendicular to the plane that contains these 3 points, and that's my normal vector. So to find the equation of the plane, I would do my n dot x, y, z is equal to n dot any of these points that I chose. Remember that formula? It's actually x minus x naught, y minus y naught, z minus z naught. And then if you collected all the d's over to the other side, and then that's your equation of the plane. So we have 16x plus 5y minus z is equal to, now I'll take this n and dot it with P1. 16 times 4? 64. 10 and 2. 76. Okay. Yeah, let's check that. Let's dot this normal vector with point 2. Yeah. Oh, it should be a plus. All right, let's dot 16. Let's dot the normal vector with P2 and see if we get the same thing. We better, right? Let's see. 16 times 2 is 32. 5 times 7 is 35. 1 times 9 is 9. 76. And we should get the same thing if we dot it with P3. Okay? So that's another way of finding the equation of a plane. Well, that's another problem that they can give you where you have 3 points and then you have to find the equation of the plane. Okay? So this one involves a cross product. Yeah?
What does that value actually mean, 76?
Well, what does the equation of the plane mean? It's not as easy like as the y-intercept kind of business, but it's somewhat related to that. So let's see. We got 16x plus 5y plus z is equal to 76. Let's attempt to graph this by hand. And the way I'm going to graph it is I'm going to graph it by finding some intercepts. So let's see where this thing crosses the z-axis. So if I want to see, okay, let's think back to 2 dimensions. If I have a line, y equals mx plus b, if I want to figure out where this thing crosses the x-axis, what do? Set y equals 0. You set the other variable equal to 0. Now imagine 3 dimensions. I have an equation with 3 dimensions, x, y, and a z. I want to know where this thing crosses the z-axis. What is the value for x and y? 0. So x and y is 0. So let's set x equal to 0 and y equal to 0 at the same time and see where the z crosses. So it crosses a 76. So in my attempt to draw this, I know my plane is going to hit the z-axis at 76. We're good so far? All right, let's play the same game with crossing the x-axis. We'll set y and z equal to 0. And what do we get? Can I get an approximation for that? I don't need to. Let's just say 19 over 4. So that's my x-intercept, and then my y-intercept would be the same thing, right? So that would be 76 over 5. So my plane would intersect the x axis, the y-axis, and the z-axis like this. And if you look at how, if you have a line in standard form, ax plus by is equal to c, you know, that's not the mx plus b form, but if it was ax plus by is equal to c, you would find those intercepts by dividing the coefficients, same way. So that's how the 76 works. Well, let's take this a few steps further, since we're talking about lines and planes. Yeah.
So the equation for the plane is that the 6x.
Yes, this is the equation of the plane. Yeah.
And do those edges of that plane, do they go off to the
Yeah, they go off in all directions.
Okay. It's just that we're like get to see kind of this shows the angle at which we're kind of oriented.
Yeah, so I'm looking at the plane in the first octant. Remember I said the first octant is the most important octant and all the other octants don't matter? Octant, remember octant? Yeah.
We're like we're drinking buttons.
X, Y, and Z are all positive, and so this is the first octant view of it.
There's a it's like quadrant connection between. That was that one class sheet.
Okay.
Yeah, sick. Oh, so okay. Damn.
So, what was I going to do now? Oh, here's what I was going to do. Let's imagine how this is going to look like on the XY plane. Let's imagine how this thing is going to look like in the XY plane. If I'm looking at the XY plane, what value do I know to be constant? So z is equal to 0. If z is equal to 0, then I'm sitting on the xy plane, right? So on the xy plane, your z is equal to 0. So if you set z is equal to 0 on this equation, then you have a two-dimensional line. And if you want to draw that two-dimensional line, there's a couple ways to do it. You can write it as y equals mx plus b, or you can find the x and y intercepts. Guess what the x and y intercepts are? We already found it here, right? So the x-intercept is when y is equal to 0, which is 76 over 5. And the y-intercept is when x is equal to 0. Wait.
Just change what you call your axis.
No, I want to call this x and y. So the x-axis is when y is equal to 0, so it's 76 over 16, which is 19 over 4. And the y-intercept is when x is equal to 0, so it's 76 over 5. And if I were to draw this line is exactly that line on the xy plane. Okay? All right. Are we good? This is cool? Pretty nice, huh? Let's see some graphics. Let's see. You want to see the actual plane in 3 dimensions? This is a parallelogram one. We didn't need a picture of that. So let's just write our 3 points. And for the points in this particular graphing calculator program, I just do these vectors. So those are the 3 points that we found. Let me go directly to the equation of the plane instead of trying to write up those vectors, because that could take a while. The equation of the plane is 16x plus 5y plus z is equal to 76. We need to do a lot more zooming out to see where they intersect. I think if I let my z go all the way up to like 80 or something, I can see where it crosses the z-axis. Can you see? So those are the 3 points, and that's where it crosses the x, the y, and the z-axis. Okay, and these points are actually on the plane. They're like oversized points, but they're on the plane. Okay, good? All right. So I think we're good with planes, yeah? This is our second time seeing it. So let's move on to lines. Now, a line in 3 dimensions is a little bit more, it's a little trickier to visualize. So let's go back to 2 dimensions. And remember that when we talked about lines in 2 dimensions, we can either be given a point and a slope, or we can be given 2 points. Let's take that idea of being given 2 points. And what I'm going to do is, instead of using the algebra way of finding equations of lines, you know, find the slope and then use a point-slope formula or whatever, let's go parametric. Remember parametric? Yeah. All right. So give me a couple of points on the plane.
Oh, he's not happy.
We could, but that's just going to make it kind of easy, special. 3, 1, 3. Let's go 3, 1. And then what else? 2, 5. So you guys, we could have done stuff on the negative. All right. Now, do you remember on a quiz that you had where I asked for the parametric equation of a line? So a line segment connecting those 2 points?
You start with your first point that you want to start off with.
Okay.
So where do you want to start?
Where should we start?
You should start at 2, 5, 1.
Let's start with 3, 1.
Okay. Damn it.
Now, what I just did was I drew a vector from 0, 0, which is why I don't want to use 0, 0. I drew a vector from the origin to the point 3, 1. Right? So, okay. I want to start at 3, 1, and then what do I do?
You minus or plus which way and how much you're 1, and for the x direction, we're going back by 1. So you're going to have minus 1. Yeah, you know what I'm saying. He knows what I'm saying. He knows what's going on. Yeah.
So, I'll draw a vector going to the other point. Let's call this vector D. So in this case, the vector D is equal to what? So in this case, the vector D is equal to what? So head minus tail. So 2 minus 3 and 5 minus 1. Okay? So that's my vector D. Now, I'm going to write down a couple of other vectors here, and then you kind of tell me or write somewhere or tell me what these vectors are about. So I'm going to write 3, 1. I'm going to write 3, 1 plus -1, 4. I'm going to write 3, 1 plus 1/2, -1, 4, and then maybe one more, 3, 1 plus 3/4, -1, 4. So, can you tell me where those new vectors are? I guess we can call them points, but you know, if we just draw a vector from the origin to the point that it's pointing to, then it's really just a point or vector. The first one is this vector over here. That's 3, 1. Where's 3, 1 plus -1, 4? That's this ending vector. Where's 3, 1 plus 1/2 times -1, 4? So is it here or somewhere else? Yes, it's here.
It's a trap. It's a trap.
So where's 3, 1 plus 3/4 -1, 4? It's what? So, what can you say about these and how can we generalize it? Well, first, what can you say about these points? They're all points on that line, right? If we were to draw our line would be this. They're all points on the line. And how would I generalize this? What's changing here? Wait, why don't I just put this here just to make it absolutely transparent?
The magnifier, or the scalar.
Scalar,
Yeah,
right? So how can I generalize this to so that I can draw the whole line? So a variable for the scalar. What variable should we use? T. Right? So if we take this and let t go from 0 to 1, then we're trapped and restricted to this line segment. That was the quiz question. You just want your t go from 0 to 1, and you're going from one point to the next point, and you just want that line segment. But if I want the whole line, what if I went beyond 1? What if I went 3, 1 plus 2 times negative 1 comma 4, where would I be? I would double this. I would be up here somewhere, right? What if I had 3 comma 1 plus negative 1 times negative 1 comma 4? So I would be over here somewhere, right? So if I don't make any restrictions to my t value, then I will call it L for line. L of t is equal to 3 comma 1 plus t times negative 1 comma 4. See that? Okay, so that's interesting. Yeah.
You can't, unfortunately, just put that in there. Like, is there a...
It's in parametric equation.
Not in, like, vector format.
If I just want to focus on the x-axis, on the x values, and focus on the y values, what's my x equal to?
4 minus 2.
I guess maybe I should. So if I just combine the x's together and the y's together, then I would have my parametric equation. Okay? Kind of want to see this being drawn out. What were the 2 points that we chose? 3, 1 and 2, 5? So if I have my equation, if I have my equation where my t goes from 0 to 1, this is what I would have, right? And if I let this go from like negative 1 to 3, then I would get more of my line. But what's really happening here, this is the cool part. What's really happening here is that as my t value changes, I have a vector that actually draws out every single point on that line. And when my t is 0, I would be pointing exactly at my first point. And when t is equal to 1, I would be pointing exactly at my second point. And I'm just drawing this out. Is that cool or what? That's so exciting. Whew. Yeah. All right. So we have an equation. We have a parametric equation in 2 dimensions that connects 2 points. What happens if these 2 points were in 3 dimensions? Would it still work? Yeah. Why wouldn't it, right? Doesn't matter where you are in space. If you have one point and another point, let's call this P1 and P2, what we can do is we can have a point connecting those 2 points as the direction vector. By the way, that's why I call it D for direction. And then we can have our drawing vector start at some point P1 and then what did we do? Plus t times the direction, not the last value, but the direction is the difference between those two points. So if you find this direction vector, you add the direction vector, you're going to be at that second point, and you scale it to any whatever value, then you can have every single point that's on this line. So this is your equation in 2 dimensions or 3 dimensions. Hell, you can even go to 4 dimensions if you want. You find an equation of a line in 4 dimensions using the same technique. You got a starting point, you got a direction between those 2 points, and then you're off. Okay? So, should we do an example? Let's find 2 points in 3 dimensions.
It doesn't matter which point you want, or you start off with, unless the direction of the vector matters, right?
Yeah, so if you don't care about which way the line is going, if you're going to let your t go from minus infinity to infinity, you're going to hit every single point of that line anyways. So it doesn't matter which way the direction goes. But if you want a specific starting point and a specific direction, that's when it's going to matter. So let's find a point in 3 dimensions. And let's have another point in 3 dimensions.
9 minus 2.
So we have 2 points. We'll find a direction vector, which is going to be the difference between them. Let's call it P1 minus, or P1 to P2.
Well, minus 9.
That's my direction vector. And then you can start on either point. Let's just go start at point 1. So P1 is minus 3, 7, and 1, plus t times 12, minus 9, and 2. So that's my line. Let's write it in parametric form. X equals
Minus 3 plus 12t. 7. Minus 9.
Okay? So sometimes the first one is called a vector form of the line. And we know the second one to be a parametric form because it has x, y, and a z. Okay? If it's 0 to 1, then we're stuck between these 2 points. So our limits will be all of the real numbers. All right? So let's go back to the two-dimensional example over here. Do you remember those problems in parametric form where they tell you to get rid of the parameter and express this in terms of x and y? What did you do? Do you remember what you did? Solve for t. So t is equal to, what is this? 3 minus x. And t equals y minus 1 divided by 4. Is that right? Mm-hmm. And then you set them equal to each other. 3 minus x is equal to y minus 1 over 4. And then you would, y equals mx plus b it, whatever. So we eliminate the parameter. Now we have an equation in what's called Cartesian form. Right? Hey, why don't we do that with, should we? Yeah, let's do it. Let's solve for t here for each one. So let's say for the first one, t is equal to x minus 3 divided by 12. Next one, t is equal to y minus 7 divided by negative 9. Plus 3. So the next one is y minus 7 divided by negative 9. And then the last one is z minus 1 divided by 2. Is that right? And then you go ahead and set them all equal to each other. Wait, there's 3 things here. So this turns out to be the symmetric form of the line. It means you can express the equation of the line without any parameters t. And since there's 3 things that it's all equal to, we'll have to call it symmetric form. So it's symmetric form of the line.
So I thought they had something to do with like symmetry.
No.
Okay.
No. Okay? Is that cool or what? So many cool things, huh? Just get so excited.
Looking at it? No, I mean realistically, how would you apply that?
Well, the same way where you eliminate the parameter here so it's not dependent on t. Here you have an x and a y and a t, so that you're dealing with 3 parameters. Here you just have an x and a y. So that's the same kind of reasoning over here. Instead of dealing x, y, z, and a t, now you just have an x, y, and z. And so if you see an equation, a couple of equal signs in there. Yeah, so, and you should be able to easily turn this into parametric equations, right? Just each of these things are equal to t, and just work backwards. So, Well, it depends on what kind of graphing device you have. Let's see if this thing graphs on this.
Can you graph that by hand though?
Nah.
Yeah.
So let's see if this thing will graph. I don't know if this thing can handle more than one equal sign. 3.
So it's just like a nice way of writing it, essentially.
Yeah.
Yeah. The parameters actually hard.
Can't graph this far. No, no. So the best way to do is that if you're given something in symmetric form is to change it into parametric form, and then you can work with it that way. Okay, let's see my objectives. Parametric equation of a line, given a point and direction, express an equation of lines using symmetric equations. Given 2 lines in space determined. Oh. Find an equation of a plane. Okay, we did this one. Find the angle of intersection between 2 planes. Oh. And the distance between. Oh. All right, good thing we have tomorrow. So tomorrow we'll finish up all these objectives, and then we'll be experts with lines and planes. See you guys.